Hello, everyone. Welcome to our 10th session, the 10th session on our data science mentor program, where we are taking an accelerated learning initiative for learning data science and machine learning. My name is Pablo. I am the founder, convener, and host of the Data Science Mentor program. The Data Science Mentor program is supposed to help folks learn and with the input of mentorship as a service. Right, and today we're going into our 10th session. Look at that over there. And today we are looking at the learning curve. And so the question is, what's the learning curve? Now it's also ideal for us to look at what we did in the 9th session, where we used polynomial regression, right, which is in a very simple fashion how the degree or degrees for which we can tune our model complexity, so that if a straight line doesn't fit through the data, then there is a possibility to get a flexible fit. So that's what we looked at. This time around, earlier on we looked at the trade-off between bias, underfitting, and variance, overfitting. Now, the next question we're going to ask ourselves is, in making a better prediction, how do we need a more complex algorithm or a more complex model, or do we need more data? So that's that's what we are going to be talking about today. Do we need more data, or do we need maybe a more complex model, an optimal model? So we're going to first talk about the intuitions and what we're doing, right? And this is called the learning curve, and I like it because it basically reflects basically the learning curve that everybody goes through in life, right? So let me look at a non-technical explanation of a learning curve. A learning curve, an intuitive, so let me call this intuitive definition. An intuitive definition for a learning curve is basically saying, look, it's like watching someone get better at a new skill over time, which means the more they practice, the better they perform. So here's the intuitive part of it, right? A learning curve, it's like watching someone get better at a new skill. Guys, remember the context is still obvious. The context here is still when the context here is ML. Input, model, output. So learning curve is like watching someone get better at a new skill. That is over time. Now, the simple philosophy here is, the more they practice, the better they become. So that's the intuition here. Now, in machine learning model, in machine learning, the model is the learner. In ML, the model is the learner. And so the intuition here is, as it sees more data, we expect the following. Expect the following. Make better predictions. Understands patterns more clearly. And reduce its mistakes. But then there's a thing, right? Also, the more it learns, as it sees more data, it could get better. But what if there's a situation? How do we get to a situation where it is more, where we know if it's more data or a complex model or another type of model? Right? These are the things we're looking at. So this is the next one. Yes. So there's a trade-off that is here. There's a trade-off. The question is, how do we know we need more data or a different / complex model? So this is also a question that the learning curve helps us figure out, right? So how do we know? So if we're talking about somebody learning, how do we know that the more they practice, the more they get better? Or should they practice something else? Or should they use a different approach to practicing? Right? So what in machine learning, we use the learning curve to measure how well model performs as we increase the size of the data. That's one. We would also use it to confirm if it's better to move or to use another model, another algorithm. That's what we're trying to do. Now, let's look here. You can see here what we did where we used polynomial regression to tune our model, right? We figured that we give it a range of tuning, polynomial tuning, and we figured out that where it started to make some sense was here, around here, because this is where it tries to make some changes. And then we now figured that if we used 3 polynomials, 3 degrees of polynomials, you can see that it will fit it well. And so now, how do we know when we ought to have more data, or when it is better to use another model? So the first thing I'm going to do, which is this question, the first thing I'm going to do is I'm going to create a data point. Now, in the last one we had created, the last data point we created here, you can see we created these data points. These are the different data points. We're going to increase these data points. You can see they're X and Y. We had created them to get started at first, right? So we're going to look at them here. You see, it's just 40. See that they're just 40 elements here. So what we're going to do is we're going to create another data point, right? At this time, when we create the data point, it will be bigger than the 40 data points we had. So I'm going to start off by saying x2, comma, y2, and we're going to use our make data function, and inside we're going to say 200 elements inside. And we can basically say plt dot scatter, open bracket, x2 dot revel, then we have y2. Oh, sorry. So you can see now, this is the data point we have. And you can see that this data point is more than this data point. Now, in order for us, right, if we plot the validation curve for this larger data set, right, would try to see the difference in the earlier data and the earlier one we had created, this one, and the very recent one. And the whole idea is to tell us, right, the whole idea is to say, with more data points, does our model perform better? And one way to find out if this is a thing is at the end, look at our learning curve, and then see, oh, okay, this makes sense. So what I'm going to do is I'm going to copy the code. I'm going to copy the code and show us. Now, in the code, it's going to have the last data point we worked on, and definitely we'll also have this very 200 data points we have. That's what we're going to do. So over here, we plot this. So the validation curve is going to have a polynomial regression and the range of the polynomial regression, which is degree here. And then we're going to see earlier on when we use the polynomial regression with this, we're able to stop at 3 here, just to say, okay, it makes some sense at that point. Now we did this, but this time you can see the first one we worked on, and you can see how it dropped off. And you can see the 2 we have here. Now, so the behavior of this validation curve has 2 important features, right? One, it has the model complexity and the number of training points. Those are the things we're looking at: model complexity and number of training points. Now, what we can do is that we can gain more insight by exploring the model behavior, right, with the number of training points. We can say, maybe if we have more training points, then maybe, right, it will help us to build a better model. Now, what that's telling us, in essence, is more data can help us when we are building our machine learning model, or we can change it. Basically, we can change it. We can change what we're doing. So it gives us two situations, and I'm going to talk about that. We're going to drop we're going to talk about what our expectations are from a learning curve. So here, this is what I'm going to write here. So expectations from a learning curve, right? So let's put this here. Now we'll start off by throwing this. A model of a given complexity will overfit a small model. So what it means is, if a model, with a model that has this complexity, it will basically figure out everything about a small data set, right? And it will perform really well on it. But on new data, it will suffer. So a model of a given complexity, say like a linear regression, will overfit a small data set, because then, right, it would understand everything about the data. Now, what that means is that the validation score will be relatively low, right? The training score will be relatively high. Now, that's one. Second, if the data set is large, a model of a given complexity will underfit a large data set, which means the training score will decrease, but the validation score will increase, right? And so the final part is, if a model will not, except by giving chance, give a better score for validation, for the validation set than the training set. So that's what it is. It's basically saying that the curves should keep going closer together, but they will never cross. So that's what it's saying. The curves will keep getting closer, but they will never cross. So that's what it is. So sorry guys, I'm trying to make sense of this note. I'm trying. I need to write this out correctly. So what it will be is, okay. Here, a model will never, a model, except by chance, model, comma, except by chance, will never give will never give a better score. Will never have a better validation score than the training score. Yeah. Or than the training set. Yeah, that's what it is. Now, what does this mean? This means that it means that the curve will keep getting closer, but they'll never cross. And so how do we know this is it, right? What I'm going to do here is I'm going to show you what I mean by saying from ipython.display import image. And so we use the same image. Oh, excuse me. And here we have file name. And here we will visualize it. So this is what we're going to be seeing. So you see that we never cross the training score. That's from the training set. And this, they will never score. They'll just you just see them be very close like this. They'll never cross. That's the conversation that we are talking about here. So what we're going to do is we're going to with scikit-learn, it is easy for us to visualize this conversation. But the notable thing we're looking at is that with the learning curve, there's a convergence to a particular score. And as the training sample goes, right, it gets that convergence. But once the model has converged, adding more training data wouldn't really do much. And so it's typically saying, look, there's a time when you're building your model, you get to know whether if you need to add more data or you need to use another model. So that's the whole idea, right? So what we're going to do, the last thing we're going to do is we are going to use scikit-learn. We're going to use scikit-learn, right, to plot two situations, right? Remember that we mentioned that you can, when we use polynomial regression, we're tweaking the model complexity. So we're going to have two situations where we compute a learning curve using the first data set, and the first data set will have like a second order polynomial, right? That first data set is small, and then we would now use the data set with a ninth order polynomial. Now, what we're trying to do here is that we're trying to look at whether at this point we deal with more data, right, by adding more training data, or what is just to look for a complexity of the model that's better. Because with the complexity of a model that is better, then we start to ask really tough questions. So and so that's just basically what I'm just trying to do here. So the first to set this going, I'll need to from sklearn dot model selection, we can import learning curve. So the next thing we'll do is we would use the object-oriented way of building code. We'll create objects to it, right? Second, we are now going to plot it. Plot and would sort of dial through the polynomial regression. What we're going to do is we're going to go through two, and then we'll look at the degree, a certain number of degree that we have going on. So what I'm going to do is I'm going to copy all of this. All right, so that's what we're going to do. So we have a degree, and we're going to enumerate between 2 and 9, so which is our polynomials, and we are now going to plot between this polynomial. We're going to plot a linear curve within this polynomials that we have set up. So we're going to run this, and then go on to plt.show. Now with this, you can see we have a 2-degree polynomial and a 9th degree polynomial. Now this basically gives us how our model responds to increasing amounts of data, right? In particular, when we look at the learning curve, right, you can see this was just very similar to what we had done earlier on, right? You can see maybe with this degree here, you can see the training size, right? With the training size here, a training size here is like maybe like 13, right? And then here our training size is massive. Now, does it perform really well? What's the convergence like? Right now, at this point, what we're looking at is we're looking at this point of convergence. This one, with a smaller data set and a 2-degree polynomial, you can see that it gets to a point where you try to tell yourself, okay, you know, this is where this is where it converges, so to speak, and say, okay, at this point it converges. You can see this very tiny line that comes in here. For this, it takes a lot of data, and still you can see where convergence would typically happen if we had a training size that was a lot more. Because with a training size that's a lot more, you can see that it has to train and learn patterns the more. And if it's training and learning patterns, then there's a possibility that it might make, some sense. Now, when plotting a curve, your particular choice of model and data sets can help you make this type of decision on whether to move forward with improving your analysis. Now, the solid line you see here, shows, maybe tells you the results that you're having, right? You can see that you can see that if you look at the validation score here, remember that your validation score isn't your training score, right, that we have over here, which typically comes all the way. Because if you look over here, what we are missing out here is basically this, right? And so here you can see that the tapering of the validation score, you can see where it's tapering from here, because it's sort of what we sort of did is like take this guide that we had here and sort of turn it the other way around, because here we're looking at where it starts to taper. Because over here you start to see, okay, it has grown and then it starts tapering from here, right? So this is what we are looking at here. So if you come over here, it tells you, right, with this 2-degree polynomial, it starts to tell you, okay, this is where we might start to say, okay, there's some form of convergence that makes some sense, right? Now, the validation score that is the validation curve that is larger, right, tells you, because this one you can see that it starts really early. This one you can see that it takes a bit of time for some things to start happening here, right, because of a lot of work that gets before this convergence happens. It's the one with the larger data sets that we're looking at. the one with the larger data set, you know, sort of makes a lot of sense. That sort of tells us that there's a lot of maybe pattern matching or pattern understanding that happens, right? And to that end, you can now tell that, and to that end, it means it will need a higher degree of polynomials to tweak it to make some sense, right? But then, right, because the data is large, it starts to make a lot of sense. But remember, this conversation is generally around what you need to do in terms of a small data set and your model, a large data set and your model, and both a small and large data set with respect to when to use another model. Because the idea is maybe you need a larger data set to find patterns in order for your data to generalize, or you need a new model, right? Or maybe what we call a much more complicated models with high level assumptions, right? To see if you would need to train it with that model in order to generalize in the situation you're trying to solve for, right? But in essence, what the validation curve does, that it's just like we mentioned, it tells you, right, is expectations that a model of a given complexity will overfit a small data. These are its intuitions, right? A model of a given complexity will underfit a large data set, which tells you, and when it underfits a large data set, it tells you that there's no difference between its training score and its validation score. Here, what we would have at this very point is that we would have a basic training score, but its validation score will be so poor, right? And here, that means it will overfit. It will memorize a lot about the small data set, but it will overfit when it sees, it will perform poorly when it sees new data. And here, because of a given complexity, it wouldn't make sense of, because of the given complexity, it wouldn't make sense of the large data set. So which means it has a basic training score and a basic validation score. So it's just there. It can't typically find the pattern, right? But also a model, except by chance, will never have a better validation score than the training set. So they will never cross. They will just, what we're looking for basically is some level of a convergence. And when it converges here, it tells you that they will converge, but it will be a good fit by the time it's telling you when it's coming here, it's being a good fit. And the same thing we're having here, you can see, right? This converges early, small data sets, training size. With a very large training size, it takes some time before the convergence happens. All right, so which means at some point we're looking at, is it overfitting or underfitting, or are we in need of a new or a complex model that will help us, find patterns good enough to generalize to a new data. So that's what the learning curve does. Again, I almost always like to set this caveat. I always like to say that even these things might look complex, I try as much as possible to let you know that learning curves help you tell if you should increase to your data. And that's, because when you train your first model, you typically want to tweak it. And if you tweak it, you want to also find out if this model is learning really well. And if you try and you notice that with the amount of data you have, that the model converged really quickly, you're wanting to ask yourself, and then you end up looking at your metrics and say, okay, is this metrics really good? Okay, is the validation score really good? what's up with the validation score with respect to the training score. Then you now ask yourself, maybe I need more data. And then you go and find more data for the situation. If you notice that your data is pretty much, and yet it's you're struggling with it, maybe it's underfitting, right? There's no difference. There's barely, the validation scores and the training score, they're just really close. Then you need to ask yourself, maybe this model doesn't typically work, right? So these things are really important when building models. Again, we've said so much technicalities, but it basically means if I am predicting the salary of workers based on some explanatory variables, at the end of the day, I want to be sure if the errors are reasonable amount of error, not that it doesn't deviate so much from the observed variables, that the predicted variable does not give the predicted variable does not differ so much from the observed variables in terms of our targets, right? And then if we have a situation where they differ so much, and that means that it's underfitting, it's not making sense of the data. If we have a situation where it tells you so much, you can predict based on the training data, but whenever you bring new data, it's having any problem, it cannot understand it. It's telling you maybe this is the right time for you to add more information to it so that we can make sense of salary earning, what it means in that space, or it's about time you tried another model. So yeah, guys, so that's that for today's session. These things will make a lot of sense. We're gradually coming close to where we do a project, and this project basically just encapsulates a lot of things, right? From your introduction to Python to how you write code, but most part is understanding why you have to solve problems using machine learning, because it's not about the technical side of things, it's about the problem you're solving, right? If you're predicting store prices for different months and different trends and different seasons, right? What kind of problems are you trying to solve for any organization, maybe that runs different stores in different cities, different time zones, and with different seasons, and different seasons meaning somebody at one end is maybe observing maybe a certain day, and in another city or another country they're observing another day. What does that mean in terms of price variation, and how do you find those optimal price variations that makes for profit? These are the kind of things that machine learning is trying to do so that you can have that competitive edge. And again, remember, it's not about the code you write, it's again about the problems you're trying to solve. So all these features we are using is the technical side to answering the real world problem. So it's just like pointers that say, I think this is what you should do, and I think you should let this go. So that is what the learning curve is. And just like life, it's like how you're learning. It's your learning curve. You're trying to tell, if it took me so long to learn this, maybe I should read more books. Or if I didn't perform so well in this test, maybe I should read more books. Or I should try a different approach to the learning. All right, so if you're live on the call, you can ask any question. If you're watching the recorded session, please feel free to drop a message in the Telegram channels. And remember, the Telegram channel is when you drop messages so that you can ask for mentorship, or you can say, look, there's something wrong and I need us to do a walkthrough. And so that's basically what the data science mentor program is basically about. All right, guys.